Okay, so in our last lecture, did I conclude with problems?
You gave problems earlier.
Okay. So I think I have some other problems to give
You
you.
ended with a corollary.
Okay, so there are some more problems that you can do is from Hoffman and Kunz. Section 1, so page 21. And problems 2, 3, 4, 5. These problems are based on our last lecture. Okay, so did you understand the concept of
Elementary matrices.
yeah? Okay, and one other thing that I concluded in our last lecture, that is the corollary. That corollary says that let A and B be M cross N matrices. So I'm considering A and B to be M cross N matrices. Over the field F, then B is row equivalent to A if and only if B equals to P. That was our last corollary, right? Where P is a M cross M elementary matrices. So I didn't give you a proper proof for that corollary, but do you get the idea of the proof? So
Subscribe.
yes, so yeah. Okay. So the idea is so P is something like EK, E2, E1, and then B is equals to EK, E2, E1 with A. Okay, so since A and B is a matrix of size M cross N over the field F, then B is row equivalent to A if B equals to P. And why we are considering this, why this is important, because in our previous lecture we defined the elementary matrices, right? And the elementary matrices are something like so E, if E is the elementary matrix, then E is equals to E of I. That was the definition. So a single ERO applied on the identity matrix will give you the elementary matrices, right? Okay. So then, actually, and what was the definition of two equivalent matrix?
Finite number of row equivalent operations.
Yeah.
Finite row
So
operations.
there should exist a finite sequence of ERO. And applying that ERO, finite sequence of ERO on a matrix B, you can deduce the matrix A, right? So the idea was something like if A and B are equivalent matrices, then A is equals to some EK dot dot E2 E1 of A. If this is the case, then then we say B is row equivalent to A, right? But in another theorem, we showed that E of A is equivalent to some elementary matrix E with A, right? So that means then this equality gives us that A is equivalent to EA. right? Okay, then if A is equivalent to EA, then considering this definition, this statement, B equals to EK dot dot E2 E1A, then so E1A, this is equals to what? This is equals to some elementary row operation E1 of A, right? Then we know that A is equivalent to E1 of A. That means this is also equivalent to E1A, right?
So that's not off, right? U1A is the matrix product.
Yeah, that's not the of. I'm just taking the product of.
So U1A.
Okay. Just for the clarification, this is the matrix product. So because E1 is a elementary matrix, and A is a matrix, so these two is actually made for the product of the matrix. Okay, and this is equals to E1A, and we know that E1 of A is equivalent to the matrix A. So that means A is also equivalent to E1A, right? Right. So so now if I multiply it with say E2 E1 of A, then this is what? This is just E sum 2 of E1A, right? But and this is also what? E2 E1A is equivalent to E1A, right? And since equivalence of matrix is actually the equivalence relation, that means the third property of equivalence relation, the third property of equivalence relation is transitivity, right? So what is transitivity? So transitivity says that if A is equivalent to B and B is equivalent to C, then A is equivalent to C, right? This is the third property of the equivalence relation.
Equivalence relation, this transitivity can be found in zero clause thermodynamics. If the two system is thermal equilibrium with a
Yeah,
then
right. So, and now consider these two. This and this. So, this one says A is row equivalent to E1A, and this one says that E1A is equivalent to E2 E1A, right?
And also write in reverse order. You can also write U1A equivalent.
Okay, so that follows from the definition of equivalence relation as well, because the first one is that what it is called? It is the reflexivity. Reflexivity is same. No, it is not actually reflexivity. It is symmetry. Yeah. Symmetry is saying that if A is equivalent to B, then B is equivalent to A. So that's why we don't need to write it in terms of E1A is equivalent to E2 E1, but you can definitely write that.
So then that's the UPI can apply.
Yeah. Okay. So for your convenience, I can write it like E1A is equivalent to E2 E1A. Okay. Then from that you can conclude that E2 So A is equivalent to E2 E1 A, right? And since I'm multiplying a finite number of E's with A, that means there is no issue with the convergence or anything, right? So that follows that of course B is equivalent to A, right? So that was the idea of the proof, but there is also another rigorous proof you can found Hoffenheim. There was a different approach of proving that corollary. You can just do it in this way using the equivalence relation. Okay, so
This Hoffenheim is page 21.
I don't actually.
The exercises are from page 21.
Yeah, the exercises are from page 21, but
These are
no, this is not the proof of. Yeah, I just give you an idea of the proof using the equivalence relation of the corollary I gave you in our last lecture. So now let us define the invertible matrices. So invertible matrices. Let A be an n cross n matrix over the field F, and n cross n matrix B B such that BA equals to I is called
so is it
no. I think you messed up with that. It was at 3. Yeah, linear algebra 3 to 6, 430p. Okay, so matrix B is such that BA equals to I is called a left inverse of A. Then and n cross n matrix B such that AB equals to I is called a right inverse of A. Now, if AB equals to BA equals to I, then B is called a two-sided inverse of A. So, why we are considering the left inverse and the right inverse?
For square matrix.
This is equivalent,
This is equivalent.
but there is a possibility that a inverse can be exist for only from the left. Okay, yes, and if you do a course on functional analysis, then you will encounter a lot of example of that some operations are defined only from the left, or some operations are defined only from the right. So in our case, in most of our cases, when we are considering the so when commutativity is exist, then actually these two things, the left operation and the right operation, mean actually the same thing, but it is possible that these two are not actually the same operation. That's why we are considering this one. Okay, so from that it is also follow a lemma. If A has a left inverse B and a right inverse C, then B is actually C. So this is a lemma. So can you give an hint how I can approach for the proof?
We can show that these two are equal.
Equal, exactly. So to
for
show that,
AB, we take AB equal to I, and we also take CA equal to, okay, sorry, BA equal to I, CA equal to, then we multiply both sides with A inverse.
okay, but you have to consider the inverse from the left or right.
Oh, yeah.
So that's why there is a problem. So the proof is very simple actually. So what you can do is, so consider B, and B is equals to, I can write it like BI, and but since I is the identity matrix and C is the inverse of A, then I can write it B times A C, and BA C, that is I, C, that is C. Now tell me this one thing, how I did that, what rules I used here. Associativity of matrix multiplication. So B times AC is actually BA times C, right? And then since B is the left inverse of A, then BA is actually identity, and identity times the right inverse C is equals to the C. Yeah, that means B is equals to C. That means when left and right inverse exist, these two are equal. Okay, so now there is a theorem, and the theorem is, let A and B be in cross in matrix. So matrices over F. So then this follows that 1, if A is invertible, so is A inverse, and A inverse is equals to A. If both A and B are invertible, so is A times B, and AB inverse is actually B inverse A inverse. Okay, So the idea is when you do linear algebra type courses, so when you read a book or something, there is always these things, these feelings that these are the uh, trivial proof, right? But you have to rigorously prove that thing. So when you are considering something like how I get this equality from this to this equality, then you have to, at least you have to have back in your mind that you are using the associativity. Otherwise, you cannot actually form a proper rigorous proof of some theorems or anything. So, okay. So, we actually want to prove that A is invertible, so is A inverse, and A inverse inverse is equals to A. That is a trivial proof, right? But
How do we do that?
yeah, so the idea is what you can
We can
develop.
use uniqueness of the A inverse. Then
True.
from that proof, we can use uniqueness of the A inverse and show that if we take A inverse,
Okay.
they both goes to I.
Okay. So the idea is so A and B are matrices of size n cross n, right? And I'm saying A is invertible. So when I'm saying A is invertible, that means A has a matrix of size n cross n that is inverse of A, right? Because the definition says that. So that means what I can write is there exist.
Is it proof that you were
Yeah, so I'm not going to prove all this theorem rigorously, but I will give you a scratch of the proof and you can, yeah. So there exists an in cross n matrix A inverse, so that inverse such that A inverse is equals to A inverse A is equals to I, right? Now consider the definition again. Let A be an n cross n matrix over the field of F and n cross n matrix B such that B equals to I is called a left inverse. And finally, there is this definition. If A, B, B A equals to I, then B is called a two-sided inverse of A. Okay. So, and okay. So, yeah, I forgot to define it. Okay, so when I'm saying the inverse of a matrix, so there is a notation. When the both-sided inverse exists, that means we'll say that A inverse is actually is the inverse of the matrix A. Okay, so we will use this notation from now, that if A has an inverse, both-sided inverse, then the inverse is actually A inverse. Okay, then so that's why I write it like this, since there so A is a invertible matrix, that means there exists a inverse A inverse, and A inverse is equals to A inverse A is equals to I. Okay, now consider it this way, that you are considering now that A inverse is your matrix and you are multiplying it from the left by A, then again from the right by A, and you are getting I, right? So I start from the definition that since A is the invertible matrix, then there exists a inverse. But now consider our matrix is the A inverse matrix, and from this equality, A is equals to A times A inverse is equals to I. So if I consider this A inverse matrix, this is what? This is also invertible. That means there exists a invertible matrix, inverse of this A inverse, and that is what? From this equality, this is actually A, right? So that means what I can do is, so inverse of this matrix, A inverse. What is the notation for this?
A inverse
A inverse inverse. That is A inverse inverse, and that is what? That is just
I into A.
just simply
A.
A, right? Because A inverse inverse, so A is the inverse of A inverse, right? That's why this is false. And the second one, this I proved in a previous lecture, right? So this is just simple. You have to just apply the definition. You can multiply B inverse A inverse with AB, and you can multiply AB with B inverse A inverse. Simply you will get because let's just consider B inverse A inverse with AB. These two, I can multiply these two using the associativity. Then you will get something B inverse IB, and this is just identity. Again, you can use the definition AB, B inverse, A inverse, and this is simply AI, A inverse, and that's it. That is identity, right? Okay. Is there any question? Afternoon. Okay. So, and we also proved something like the finite number of multiplication of matrix, and if you take the inverse of that, that has a inverse, right? So, like something A1, A2 dot dot AK inverse is equals to AK inverse AK minus 1 inverse A2 inverse A1 inverse. You can prove this theorem using the induction. You have to take this as a matrix multiplication, then you can apply the previous definition like this one, sorry, this theorem, and then your proof will follow from that picture. Do you have any question? Okay. Now there is another theorem. An elementary matrix matrix is yeah. Which one? This one? This one? Okay. So okay. So the idea is so we already saw that AB inverse is equals to what? B inverse A inverse, right? So just take it this way: A1, A2, then A2 inverse, A1 inverse, right? Now, so I can apply the induction method here, right? So what was the induction hypothesis will be? So let's take as a hypothesis, this is A1 dot dot a some number m inverse is equals to AM inverse. So then I can define A1 to AM as a matrix of P. So P will be something like A1 dot dot AM, right? And so P inverse will be what?
AM inverse.
And P inverse is just simply AM inverse A1 inverse. And then what will be this? A1 dot dot AM, then AM plus 1 inverse is simply P AM plus 1 inverse, and use the definition of previous theorem. This is what? AM plus 1 inverse P inverse, but P inverse is this, then this is AM plus 1 inverse AM inverse dot dot, right? So we can show that if for any m this satisfies, then m plus 1 also satisfies. Okay. So yeah. Now theorem. An elementary matrix is invertible. That means this says that for every elementary matrix there exists an inverse matrix, and if you multiply this with the inverse matrix, you will get identity. Right? Okay, so how can you prove that? So we know
There exists elementary row, inverse of elementary row.
exactly. So the proof, the sketch of the proof is something like. So what is the definition of elementary matrix? So this is E equals to some elementary row operation of the identity matrix, right? Okay, and we're not considering a specific elementary matrix. This E can be any of the 3 elementary row operation. This can be the type 1 row operation, type 2 row operation, even the type 3 operation. Okay, so E equals to EI, then what we know is actually that, okay, so we know that for every elementary row operation, row, there exists an inverse row, and let E1 is the inverse of the row E. Okay. So we know that for every row there exists an inverse row, and I'm considering that E1 is the inverse row of that elementary row operation E. Okay. So then what is E1? E1 is actually E1 of I, right? Does it make sense? It's just a definition. So yeah. Okay, so I'm considering.
So for every arrow there exists an inverse arrow.
Yeah, we proved it in a previous lecture.
Inverse arrow gets back the original.
Yeah, so
It's
the
like I do a row operation and just say reverse.
yeah. So and why this is possible? So the one thing that we are considering the field, right? So the first row is something like what? E1 of A. This is not the one of these. E of A, and I am considering E first type of row. Then this is what? This is just, if I consider Ij, this is just Aij if I is not equals to R, and Eaij, Rj is equals to C times A Rj. That means, yeah, no, this is the first one. So I just take the product of the element Arj with a fielded element, right? And C is the element C that is non-zero and belong to the field. And
I have a question. Why do we always take non-zero? Because C for 0 R is the field does not contain 0 for multiplication.
no, in the definition of field, what we define as a field is that for every non-zero element in the field, there exists an inverse of that element.
Multiplicative inverse.
Yeah, multiplicative inverse. If you consider the 0 then 1 over 0 is actually what? This doesn't exist. That's why we have to take non-zero element that belongs to the field. For every non-zero element in the field, there exists a unique inverse of that element.
That means multiplication by zero is not defined for the field.
0 multiplication by
Because
0.
zero has an inverse element in that field.
Actually, you can actually take the multiplication 0 with 0.
But we are not taking it because of our definition that existence of inverse.
Yeah. Right. So then this is equals to ARJ. Zoom out. Okay, so why we can take the inverse operation of this type? Because C belongs to the field. That means for every non-zero C that is an element of the field, there exists a C inverse, and that is what? 1 over C. So the inverse operation will be what? I can multiply this row by 1 over C, and I can define that as a operation E1. So if I define it, E1 of Aij is equals to just Ij if I is not equals to R, and E1 of A Rj is equals to 1 over C A Rj. Now if I apply E1 of E of A and I consider the Rj element, because Ij is always same, so I am considering Rj, this is equals to what? So this will be 1 over C times E of A Rj. And what is E of A of Rj? C times, sorry, 1 over C times C A of Rj, and this is A of Rj. That means for every elementary row operation, there exists a inverse operation. Is that okay with you? Okay. So, okay, so that means this definition actually makes sense, right? So we are starting from this E equals to EI, where E is the original elementary row operation. So, and we know that E is a what? Elementary matrix, and an elementary matrix can be found by applying the ERO just one times on the identity matrix, right? Then this definition follows from the definition of the elementary matrix. Then for this E, I can define a inverse operation of this E, right? Because for every ERO there exists a inverse operation. That means for this E, I can define a inverse ERO, that is, I defined it as E1. Now, if I apply this E1 on the identity matrix, then it will give me another elementary matrix, because E1 is also a ERO.
Yeah.
And so if I apply it on the identity matrix, then this will give me the elementary matrix E1. Okay. Then what I can do is I can take the multiplication E with E1. Yeah. So E with E1, this is what? This is, we know from the definition that E times, yeah.
I think we could have put as A.
Why?
Because we will be doing elementary operations inside of a matrix. Like say,
Yeah.
parameters of function. So
Actually, we don't. We need. So, okay. So no, we don't. Let me give you why we don't. So, in the previous lecture, I give you a theorem. The theorem was that E, B, and ERO and E be the M cross M elementary matrix, then E equals to what? EI. We know this.
Oh, that's right.
Then for every M cross N matrix A, we know that E of A is actually EA, right?
Okay, we consider identity matrix in this.
Yeah.
Yeah.
Does it make sense?
Yeah.
Okay. So E1. So I'm multiplying E with E1, and using this, I can write E1 equals to this one, right? So compare these two definitions. Does it make sense? Okay. So now this is what? This is just, sorry. So E1 is equals to E of E1, and E1 is what? We define it.
E1 is E1.
This is the definition of E1, and this is what? E1 of I, but E1 is what compared to E?
They are inverse.
So I defined E1 as the inverse of the operation E. Fire? Yeah. Okay. So from this definition, since E is inverse to E1 and E1 is inverse to E, then this is what? This is just the identity matrix, right? And also this also makes sense. This is also equal to identity matrix, right? So what we conclude from this is elementary matrices are invertible, because there always exists a E1, and if you multiply this E1 with the elementary matrix E, then you are getting identity matrix. That means elementary matrices are invertible. Okay. Okay, so there is another theorem. If A is a n cross n matrix T the following. Do you know what this means? TFAE. Okay. So this is actually the following.
What is TFA?
Yeah.
Oh,
TFAE stands for this. If A is an n cross n matrix, the following are equivalent. The first one is A is invertible. Two, A is row equivalent. To the n cross n identity matrix, and the final one is A is a product of elementary matrices. So these three, E1, E2, sorry, E1, 2, and 3, these are equivalent statements. Okay, so when we are considering the equivalent statement, you have to keep in your mind that we have to start from some statement, like A is invertible matrix. Okay, so if you start from taking by taking A as an invertible matrix, then this will follow that A is a row equivalent to the identity matrix. Okay, and that will also equivalent to A is a product of elementary matrices. And if you start from another one, like A is a product of elementary matrices, then you can prove actually that this is equivalent to A is invertible. Also, all these three statements are equivalent. Okay. So if I start A as an invertible matrix, then this is what?
If invertible matrix, then it is equivalent to, yeah, because there are finite operations, we can get an identity.
Yeah. So the idea is a scratch of proof is something like we can consider that since A is what? A is a n cross n matrix, right? So every matrix is equivalent to some row reduced matrix. Yeah. So row reduced echelon matrix. So I'm considering R is the row reduced echelon matrix, which is row equivalent to A. Okay. Then using the definition of the elementary matrices, we know that so R is row equivalent to A. That means there exists a finite sequence of ERO. If I apply those ERO on matrix A, then I will get R. Okay. So, and if I translate this definition using the elementary matrices, then this will be what? R is equals to EK times E2 E1 of A. Yeah. Right? Does it make sense? Why?
Also, we need to go over.
No. So we know that two matrices are row equivalent to each other if I can so if I can extract the, so just consider let B is row equivalent to A. That means B equals to what? You can apply a finite sequence of ERO on the matrix A, and then you will get B. Then that means EK, E2, E1 of A, right? So, but from this theorem, we know E of A is equals to elementary matrix E times A, right? Then I can just translate this as what? EK, E2, E1 of A will be E1 of A. Then this is just EK, E2, E1 of A, right? So this is the definition I am considering. So just consider this to be R. Okay. Now R equals to this, then, and in a previous theorem, I proved that every elementary matrix is invertible, right? Then what I can do is I can multiply each from the left by some elementary matrix EK inverse. I can start with EK inverse, right? So this will be what? EK inverse equals to EK inverse EK, then E2 E1, with A, right?
Would there be an R?
Yeah, sorry, there is. Okay. So this is just what? This is just the identity matrix, and you can take this operation again and again, right? And then A will be what? E1 inverse, E2 inverse, EK inverse with R, right? And we also proved that the multiplication of invertible matrices is also invertible, right? You just ask that question. So I give you a scratch of proof, this one, right? So this is equals to this. It shows us that invertible product of invertible matrices is also invertible. Then using that theorem, what I conclude is this matrix A is invertible if all these elementary matrices are invertible, but the invertibility of A depends only on what? R, right? Because all these elementary matrices are invertible. That means you can definitely take the inverse of these invertible matrices. But the invertibility of A depends only on the matrix R, right? So since it depends only on R, then we have to show that R is actually what? A invertible matrix. And since R is row reduced echelon matrix, then what is the definition of row reduced echelon matrix?
Yeah, leading one.
Yeah, so
First non-zero row, it will be first
so for every non-zero row, there
First.
exists a first non-zero entry is the leading one, and all the zero rows are in the bottom of the matrix, right? So, and simple example can be like something 1 0 0 0 0 1 0 0 0, and just consider 0 0 0. Okay, so this is a row reduced echelon matrix, right? So is it possible that this matrix is invertible? No, because there are some zero rows in the bottom of the matrix, right? So if R is invertible, then it has to be so R cannot have a zero row, right? So if R is not R doesn't have a zero row, then it follows that so because if R there are no zero rows in R, then this is something like 1 0 0 0 0 1 0 0 0 0 1 0 right. That means R is the identity matrix. So since R is the identity matrix, this gives us that A is the product of these elementary matrices. So this is just what? E1 inverse, E2 inverse dot dot EK inverse, right? And there is a identity matrix, and if you construct a matrix by applying the elementary row operation or the elementary matrix on a matrix, and for our case this is I, so A is row equivalent to the identity matrix, right? Is that clear? That means A is row equivalent to I, and this gives us the proof that A is row equivalent to the identity matrix. So if I start with A as an invertible matrix, then this is what? This is just the row equivalent matrix, row equivalent to the identity matrix. Okay. So, and also we show that A is a product of the elementary matrices. Why? Because this is just what? right?
I also have to.
So that means A is equals to A is E1 inverse, E2 inverse, dot dot, EK inverse, and we don't have to consider the I, and still I is also a elementary matrix, right? So A is just this, and this is a finite product of the elementary matrix.
Can you please take the argument again why R equal to I?
Okay, so A is equals to this.
Yeah.
And now we know that every elementary matrix is invertible.
Yeah.
That means these products is also invertible. But we don't know what this R is, right?
Yes.
So if I start with A as an invertible matrix, then this R has to be an invertible matrix, right?
Yeah.
Otherwise, I cannot conclude that A is an invertible matrix, right?
Yes.
Since A is invertible, this gives us the clue that R has to be invertible matrix. But I start with R as a row reduced echelon matrix. But for a invertible row reduced echelon matrix, that is just the identity matrix. Because for row reduced echelon matrix, and we know that there are rows that are zeros and non-zero rows. But for invertible row reduced echelon matrix, it has to be what? I, because all the zero rows, there will not any zero rows in the row reduced echelon matrix, invertible row reduced echelon matrix, right? That's why this follows. Okay, so that is a proof, sketch of the proof actually, and this also gives us another corollary. Corollary: if A is an invertible n cross n matrix and if a sequence of errors reduces A to the identity, then that same sequence of operations find applied to I yields A inverse. This is a very important corollary here. So it says that if A is an invertible n cross n matrix and if a sequence of errors reduces A to the identity, then that same sequence of operations when applied to I, that means the identity matrix, yields the A inverse. And this corollary will be used to compute the inverse matrix. Yeah. So I don't think I have to prove that this corollary, just a simple scratch of the proof. And we know that A is what? From the previous theorem, we know that A is E1 inverse, E2 inverse, dot dot, EK inverse, right? And this is a multiplication of invertible matrices. That means the elementary matrices are invertible. We know that, right? And then I can take the inverse of A, and this will be what? Just simply EK plus 1, sorry, minus 1 e2 e1, right? Now let's just check a times a inverse. This is what?
Say inverse
Identity, right? So that means it's just something like ek, sorry, so this is e1 inverse, e2 inverse dot dot ek inverse with ek minus 1 e2 e1, and I can take the associativity, and this is just identity. But how did I get this A inverse?
using a previous theorem that finite multiplication.
Yeah, invertible. But we have to consider that A is the product of the invertible elementary matrices. E1, E2, Ek, but A is just what? E1 inverse, E2 inverse, dot dot Ek inverse times the identity matrix, right?
Yeah.
That means, so Ek inverse is what? The inverse operation of Ek, right? So I am constructing this A inverse, applying the inverse operation on what? On just the identity matrix. That means from this corollary follows that if A is an invertible n cross n matrix, and if a sequence of EROs reduces A to the identity, then that same sequence of operations when applied to I yields the A inverse. Does it make sense? Okay.
Okay.
Yeah. Okay.
Same means inverse of ERs, but we are applying only ERs,
Yeah.
not inverse of ERs.
No. So the idea is, okay. So I am doing what? So A, if you apply, so you see this line.
Yes.
So how did you get identity matrix from A? You have to apply first E1 inverse, sorry, E1, then E2, right? So the idea is how can you get identity from the matrix identity from A? So I is equals to Ek E2 E1 of A, right? So you can use the same definition from this, right? Does it make sense?
Yes.
Okay. Anyone have any question? Okay. So now there is another corollary. And it says that let A and B be M cross N matrices, then B is row equivalent to A if and only if B equals to P, where P is an invertible M cross N matrix. So this is just a corollary. We proved a somewhat same theorem previous in our previous lecture. Okay, so the previous lecture was something. The theorem was okay. So it was the theorem that yeah, I started with this theorem today. So that was okay. So
Then the theorem is started.
yeah, so it was not actually a theorem; it was also a corollary. I proved. So no, there was a corollary also. So this is the yeah. If A and B, sorry,
That's the theorem.
A and B to be m cross n matrices over the field F, then B is row equivalent to A if and only if B equals to PA. And just this is actually the final corollary using that corollary. M cross n matrices, then B is row equivalent to A if and only if B equals to PA, where B is an invertible M cross n matrix. Okay. Then okay, so there is another theorem, and we are going to conclude this section for an n cross n matrix, n cross n matrix A. The following are equivalent. 1. A is invertible. 2. The homogeneous system. 'Ax equal to 0 only has trivial solution. Solution x equal to 0. The system x equal to y has a solution x for each n plus 1 matrix Y. Okay. So this theorem says us that if A is invertible, okay, finish the writing. Okay, so this theorem says us that if A is invertible, then from using the previous theorem, where I show you that A is equivalent to the identity matrix. So if A is invertible, then A is equivalent to identity matrix, and then Ax equal to 0, this system has the same solution of Ix equal to 0, since A and I are equivalent matrices, right? But Ix equal to 0 has only the trivial solution. That means Ax equal to 0 also have the trivial solution. And this follows that the homogeneous system Ax equal to 0 only has the trivial solution, x equal to 0. Okay. Now, for the third case, the system Ax equal to y has a solution x for each n cross 1 matrix y. Okay. So let's start with the So what I can show you is okay. So in the forward direction, if I using these two, A is invertible, then the homogeneous system Ax equal to 0 only has the trivial solution. Okay. So since A is invertible, then AX equals to Y. Since A is invertible, from this, what we can conclude is there exists a A inverse such that A inverse A equals to A inverse is equals to identity, right? So everyone familiar with this notation?
There exists.
Yeah, there exists. And yeah, and also I can actually put a explanation. So there exists a unique A inverse. Inverse is always unique for the matrix, right? Yeah, so A inverse, that A inverse A equals to A inverse is equals to I, identity matrix. So I can multiply this equation AX equals to Y both from the left by A inverse, and this is simply what A inverse A equals to sorry I, and this is just sorry Ix equals to this is Y, and this is A inverse Y, and X equals to A inverse Y. That means for every Y of n cross 1 matrix, there exists a solution X, right? And in a backward direction, I can also show that this is true, but I don't want to go there because this will take a lot of time. So the idea, yeah, I can give you an idea of the proof. So let us consider that R is the row reduced echelon matrix, which is equivalent to A. Okay, and we wish to show R equals to the identity matrix. This is the idea. So what I can do is I can choose a n cross 1 matrix 0 0 1 such that Rx equals to E. Okay, and why this is exist, why I can construct such an E such that Rx equal to E, because so since R is row equivalent to A, that means what? R equals to some PA. What is P here?
Elementary
Products of finite elementary matrices, right? So, and from this, and we know that P is invertible, right? Because P is the product of the elementary matrices. That means this is also invertible. Therefore, Rx equal to what? Okay, so therefore, Rx equals to E gives us PAX equals to E, right? And AX equals to P inverse of E, right?
Yeah.
Does it make sense? Okay, then yeah, so I can take the Y to be what? P inverse of E, right? That means I can actually take E to be 0 0 dot dot 1, and I can construct the Y, right? Okay, so then okay, so once we have Rx equal to E with E equal to this, so once we have Rx equals to E where E is just 0, 0, dot, 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 1, then the last row of R can be 0 row at the bottom. Does it make sense?
Cannot be 0.
Cannot be 0 because what? R is a row reduced elementary matrices, right? And R equals to E, the last element is what? 1, and that is a constant, right? So if you multiply R with X and the last row of R is 0, then the multiplication Rx will give you what? 0. But that is not equals to 1. But I construct the R in such a way so that the multiplication R with X will give me this E. Okay. Does it make sense? Okay. That means the last row.
Everything else can be 0 except the last one.
Yeah. Right? But if the last row of R is non-zero, then is it possible that every other row above the last row 0? Because in a row reduced echelon matrix, we know that all the 0 row is in the bottom of that matrix, right? So we actually conclude from this that R cannot be a row reduced echelon matrix if all the rows above the last row is 0. That means if we construct all these things by using this E, then actually R has to be identity matrix, right? Okay, so that is the idea. Then that means R is equal to what? R is equals to the identity matrix, right? And this we want to prove this. We wish to show R equals to R, right? We want to show that R equals to I. Why? Because we started from that, A is invertible. And in our previous theorem, we proved that if A is invertible, then A is definitely row equivalent to the identity matrix. And we proved using the last statement that R is actually what? Identity. That means that means A is equivalent to I, and that gives us the first statement. A is invertible, right? Okay. So now let me give you an example of algorithm for computation of A inverse. A inverse. So in a previous corollary or theorem, I forgot. Yeah, corollary. One of the previous corollary we consider. Yeah. So if A is an invertible n cross n matrix, and if A is a sequence of E arrows reduce A to the invertible identity, then that same sequence of operations when applied to I yields A inverse. Okay. So we are going to use that corollary to find out the A inverse. Let me start with A matrix of 1, half, 1/3, then half, 1/3, 1/4, 1/3, 1/4, and 1/5. This is my A, and I want to find A inverse from this matrix. Okay. So what I can do is 1/2, 1/3, half, 1/3, 1/4, 1/3, 1/4, 1/5, 1 0 0 0 1 0 0 0 sorry 0 1 0. Now what I'm going to do is I will construct the row reduced echelon matrix in this part, and I will apply the same ERO on this part, and this will give me the inverse of A in the left hand side. Okay, so okay, you can do the calculation at home. I just give you the, so for the first law, do I need to do anything? No, because the first non-zero entry is already 1. That means this is the leading one for the first row, right? So for the second row and the third row, what I'm going to do is I'm going to multiply minus half with row 1 plus R2 equals to R2 prime, and minus 1/3 R1 plus R3 equals to R3 prime. Okay, and this will give me something like 1/2, 1/3. The second line is 0, 1/12, 1/12, 0, 1/12, 4/45 with 1 minus half, minus 1/3, 0, 0, 1, 0, 0, 1. I'll get this. Then what I need to do in this step?
Going to do first we have to multiply 12 in
Yeah, so I have to make this a leading one. Then I'm going to multiply this row by 12. Then this will be 1/2, 1/3, 1 0 0 0 1 1 minus 6 12 0, and this is 0, 1/12, 4/45 minus 1/3, 0 1. Okay, so the operation is sorry, I forgot the operation. 12 with R2 sorry equals to R2 prime. This was the operation. Okay, now I have to make this 0 and this also 0. Why? Because for a non-zero column, only the leading one is the non-zero element, and every other elements are 0. Then the operation will be minus half R2 plus R1 so equals to R1 prime, and minus 1/12 R2 plus R3 equals to R3 prime. Okay, so this is the operation. Then you will find that 1 0 minus 1/6 0. No, I cannot. So you can do that at home. So I'm just giving you the concept how to do it. 1 1, so there is 4 minus 6 0 minus 6 12 0 0 0 1/180 1/6 minus 1 Just note down the operations and you can do it at your home. So finally, what I need to do, I can multiply the third row 180. So 180 R3 equals to R3 prime, and this will give me 1 0 minus 1 over 6 4 minus 6 0 0 0 1. Sorry, 1 minus 6 12 0 1. This is just 30 minus 180 with 180. This is, then the operation will be something like 1 over 6 R3 plus R1 equals to R1 prime, and minus R3 plus R2 equals to R2 prime. Then this will be the identity matrix 1 0 0 0 1 0 0 0 1, and the right hand side will be 9 minus 36 30 minus 36 192 minus 180 30 minus 180 with 180. Okay, so the A inverse is this part. Okay, so A inverse is 9 minus 36 30 minus 36 192 minus 180 30 minus 180 180. This is the inverse, and you can check that this actually false. Okay, so the problems you can do is, again, these are from Hoffman and Kunz. Kunz, page 26, problems 1 2 3 4 5 8 and 12. Okay, okay, did you note down it?
Yeah.
Okay, so now let's start the definition of the vector space. Actually, we'll start the discussion of the vector space from today, and this is vector space. So the vector space definition, unless you have a proper definition of vector space, you cannot say which element is a vector or which element is not a vector. So this definition generalizes the idea of physicists and computer science scientists, that what they are saying that something has a direction and magnitude is a vector, and the CS people say that like the list of something is actually a vector. All these definitions, actually the generalization of, so this is the definition that generalizes all this idea. So, and I will give you some examples why we are considering this definition, because just these two idea, or the notion of vector, like vector has magnitude and direction, and vector is something that is actually a list of something. This is not just, these are two, yes, these are two vector, but this is not just the whole scenario. So a vector space, a vector and a vector space is something way more bigger than these two definition or idea. So definition of vector space. So a vector space consists of the following. First one, a field F of scalars. 2, a set V of objects to be called vectors. And the third one is a rule or operation. Operation called vector addition. Which associates with each pair of vectors u comma v belong to the vector space V a vector. Okay, so we are following this notation. A vector u plus v that is also belong to V called the sum of u vector and v vector in such a way that for u v w belongs to V, the following are fulfilled. Five minutes. So the first one is the addition. Is commutative. That means u vector plus v vector equals to v vector plus u vector. The second one is associative. So this is u vector plus v vector plus w vector is actually u vector plus v vector plus w vector. So there is another one C. There is a unit vector, unique vector 0 belongs to V called the 0 vector. Vector such that u vector plus 0 vector is actually u vector for every u belongs to P. Is everyone familiar with this notation as well? This is for all or for every? This means this notation. Okay, so then there is a D for each u belongs to V. There is a unique vector minus u belongs to V such that u vector plus minus u vector is equals to 0. Okay, so can you tell me why I didn't write u vector plus u vector also equal to 0? Because
As an associative. Commutative.
commutative.
Sorry.
So since I already defined the commutativity, that means I don't have to write in that way. And there is another rule for a rule or operation called scalar multiplication. Which associates with the pair C, u vector with C belongs to the field F and u belongs to the vector space V. A Cu belongs to vector V called the scalar multiplication of C and u in such a way that the following hold for any C1, C2 belongs to field F and u, V vector belongs to the vector space V. A 1 times the vector u is u for every u belongs to the vector space V. B C1 C2 times the vector u is equals to C1 C2 times the vector u. C u plus V is equals to Cu plus Cv and D C1 plus C2 with the vector u is equals to C1 u vector plus C2 u vector. If all of these are fulfilled, then the set
Yes, sorry. Sorry, 440.
okay then the set Yeah, set V is called a vector space over the field F. Okay, so this is the definition of the vector space.
Very deep definition.
Yeah, but so before I finished, I want to give you. So I actually remember this CANI, Kenny and Edu.
Like this,
Yeah, so this is commutativity
good mnemonics.
and this is associativity. This is neutral element. This is the inverse element. All these four operations are the addition.
So
And
that's the
given
basic thing. One is what when you say commutative.
yeah, C is for commutativity, A is for associativity, N is for neutral elements, that is the zero,
So this is zero.
and I is the
And the
inverse. Yeah. And for the second one, A is the associative of multiplication.
Of the scalar product.
Yeah. So and D is for distributivity, and there are two distributivity blocks.
I can distribute. Right?
Yes. So the first one is this, and the second one is this. Okay.
So associativity is which one? This one.
This one is the B is the associative. The C and D are the distributive, and last element is the
Unit.
unit. Yeah.
Unit.
Unit. So unit is the this one.
The first one.
Okay. Okay.
Okay. Good mnemonics.
Okay.
Good for example.
Okay. That's all for today. Thank you very much.